Anybody used a hot water bottle before? You know what that is? It's like a flexible sort of bottle that you put hot water in to put on your sore muscles, or you keep it in bed with you to keep you warm in the winter. So a hot water bottle contains 725 grams of water at 65 degrees C. The water cools to body temperature as you put it on your skin. How many kilojoules of heat could be transferred to your sore muscles? So how did you go about doing a problem like this? What kind of an equation are we going to use here? What's going on here? Yeah. Did anybody do this one? I think this was listed in the homework. We've gotten to it. Yeah.
We have to find the change in temperature first.
Right. So you've got a certain amount of water that is changing temperature. And anytime you have a mass of something that's changing temperature, you want to know how much it's changing by, because we know that 1 calorie is the amount of energy it takes to do what? Remember that definition? What is 1 calorie?
Heat 1 gram of water.
Right. How about how much?
1 degree.
Right. So 1 calorie heats 1 gram of water, 1 degree C. Right. That's how we define a calorie. So if we have 725 grams of water and it's moved some other change in temperature, we can multiply those numbers together and get that same equivalent. So the official equation, if you want to put it in that term, is that heat is the mass of whatever's being heated times that change in temperature, which we call delta T, times the specific heat. And to follow the units, mass is in grams, delta T is in degrees C, and then specific heat is usually calories per gram degree C, but could also be joules per gram degree C if you have a different specific heat. Yeah?
And this is like for measuring heat in calories?
Right, because this unit is in calories. So if you wanted a different unit, you have a couple choices. You can use a different specific heat, like if you have a table of specific heats. Let me show you what that looks like. That's in the book here.
Okay, so the number, when you get mass times the change in temperature, that will be, like, that number is calories then?
No, because you also have to multiply by the specific heat. So let me show you. Here's a table.
Okay.
Here's specific heats for some substances. So like water. If you use 1 for the specific heat, you're saying 1 calorie per gram degree C. But you could also do the equation with 4.184 joules per gram degree C. And then you've got your answer in joules instead of calories. So as long as you follow the units, it'll work. So like in my example here, grams will cancel with grams, degree C cancels with degree C, and so we're left with calories. I usually think about it in calories because that's an easy number to remember. It's just 1 calorie per gram degree C. If you want to remember the 4.184 joules per gram degree C, that's fine too, but 1, I don't know, seems like a nicer, more even number, so I usually go with that. We can always convert it to joules later if we can look up a conversion factor. In this case, we will, because this question is asking us for kilojoules of heat. So if we get the answer in calories, we'll have to then convert it to kilojoules. All right, so that said, how do we plug these things in there? What is our mass in this question? Yeah, 725 grams. And what's our change in temperature? Yeah, 28 degrees C. 37 to 65, that's 28 degrees. So 28 degrees C. And then our specific heat is 1 calorie per gram degree C. Because it's water. If it were a different substance, we might have to use a different specific heat. But if it's water, we can just use 1. All right, so we multiply those numbers together. Can't do that one in my head. So that's 725 times, whoops, 725, hold on, 20,300. Thanks. And then we have to always keep in mind our units. Grams have canceled, degrees C have canceled, so that is calories, little c calories. So that is the amount of energy that the hot water bottle has transferred to the muscles, but the question is asking us to report that number in kilojoules. So I think of, you can all do all this together. If your brain is a couple steps ahead of us, that's fine. I like to think of it as 2 separate problems. First, we're going to solve for the heat transfer in calories, because that's what how we usually do it, and then we can convert those calories to joules in the same way we did all those conversions before in previous chapters. So to do that, we would start with a plan, and we would say we're starting with our calories that we found, and we're going to go to something into something and eventually to kilojoules. What's going to be our intermediate step, since we don't know a conversion between calories and kilojoules? Or we can't necessarily look that up. So where would you go in between? Probably joules. We can look up calories to joules, and then we know joules to kilojoules because we know that there's got to be 1,000 joules in a kilojoule. That's what that kilo prefix means. All right, so if that conversion is set up, now we just need to do the calculation. So it's 20,300 calories. And then we're going to set up our units in 2 more fractions to cancel the unit we don't want and get the unit that we do want. So in the first case, we're going to cancel calories and turn it into joules, because that's what our little map above told us. Go calories to joules. That means calories goes to the bottom and to joules on top. That allows calories to cancel with calories. And then we're going to go from joules to kilojoules. And that will allow the joules to cancel. And then our final answer will be in kilojoules. So that joules to calories, you may not know that number. That's fine. That's a number that would be given to you. It's 4 points. You can look this up. 4.184 joules per 1 calorie. And then we also said that there were 1,000 joules in a kilojoule. So to calculate that out, we take our 20,300, we multiply by 4.184, and then we divide by 1,000, because the 1,000's on the bottom. And that tells us that our final answer should be 84.9 kilojoules. So 84.9 kilojoules of energy to transferring from the hot water bottle to the muscles. So from the standpoint of the hot water bottle, if the hot water bottle is the system that we care about, is this an exothermic process or an endothermic process? Exo, why? Yeah, because the heat is going out from the water bottle to the muscles. If the muscles are our system, if the muscles are what we care about, where our frame of reference is, then it's an endothermic process because the energy is coming into the muscles. So exoendothermic depends on what you are looking at. All right, should we try another one like that? There's something similar? Okay. So let's look at one that's a little bit trickier, more like one of the problems from the lab. Whoops, that's the answer. Just trying to find where this. Oh, you know what? It's up here. Sorry, I'm zoomed way in, so it's taking forever to get through the pages here. Oh, there's one. Okay, let's try this one. So this is similar to a lab type calculation. You can see how the book goes through this as well, but we'll look at it. Good example of this type. So probably the hardest question in the lab was the last one, where it asks you to look at how some steam cools and how much energy is released. And the reason that that's hard is it actually combines two types of calculations. Because first you have to look at what happens when the steam condenses, when it turns from a vapor to a liquid. I'm talking about this lab 3, by the way. Vapor to a liquid. And then you also have to calculate the cooling energy that we just did right here. Same kind of thing. So you have one of these types of problems, but then you also have the other type of problem. So let's take a look at this, and I'll show you some strategies to break that up. Calculate the total heat in joules needed to convert 15 grams of liquid ethanol at 25 degrees C to gas at its boiling point of 78 degrees C. And then it tells you the specific heat of ethanol and the heat of vaporization of ethanol. Ethanol, or ethyl alcohol, is the traditional alcohol that we get from fermenting sugar. And that's what they're talking about here. So let's look at a couple key words here. First of all, convert. Convert tells you that there's some change going on. We're not simply heating or cooling something, we're changing it. In this case, it's a physical change. We're converting that ethanol to a gas. So we're converting liquid ethanol to gas, which means that there is a phase change happening here. We're not just heating it up, we are changing it. So that actually requires 2 steps. First, we have to heat it up, and then we have to boil it. Recall the energy curves from last class, and from the lab that you made, where you would heat something up. So here was energy versus temperature. And you're heating something up and heating something up until it gets to the boiling point. Then you have to continue to put more energy in, but you don't change the temperature. And you saw that in the lab. When you heated the water up, you added heat by having the burner going. But then once you got up to the boiling point, the temperature stayed constant, right? Around 100 probably. Because now you're boiling it and you're putting that energy in to boil the water, not to heat it up anymore. So we're going to treat these differently because they're different types of calculations. We'll say this is the heating or the warming of the ethanol, and then this is the boiling. The warming part is another problem exactly like what we just did. We have a certain mass of a substance and we're warming it from one temperature to another temperature. So we take its mass, we take the change in temperature, we take the specific heat, we multiply them together just as we did before. So I'm going to simply copy my equation from up here. Oops. Down here. Because it's the same. We're gonna use the same equation for that blue part. Now those 3 numbers are going to be different. What's our mass of the ethanol? See, we can look up there. 15 grams, right? 15.0 grams. And what's our change of temperature this time? $53 degrees, right? And the specific heat is different too, because we're not dealing with water. So it's not just one. We're not even given a specific heat in calories. This time we're given it in joules. So that's 2.46 joules per gram degree C. So 2.46 joules per gram degree C. All right, I'll put those together. 15 times 53 times 2.46. And we get, we'll just round it and say 1956 joules. Note that that's joules, not calories, because our specific heat was in joules. And that's how much energy it takes to heat the ethanol up from 25 degrees to 78 degrees. But we're not done, because it doesn't say how much heat is needed to heat the ethanol up or to warm the ethanol from 25 to 78. It says how much energy is needed to boil all the ethanol, to convert it to a gas. It doesn't actually say boil, but it says convert to gas, which we understand as boil. So we need another step now to see how much energy that takes. So the energy to boil is going to be the heat of vaporization that is how much heat in joules or calories per gram. So how much heat does it take to boil 1 gram of the substance, or to convert 1 gram of it to gas? But we have more than 1 gram, so we're going to multiply that by the mass in grams. So grams will cancel, and we'll just end up with joules in heat. All right, so based on our problem here, our heat of vaporization is given. That for ethanol, that is 841 joules per gram, per 1 gram. And we are multiplying that by 15 grams because all of it has to boil. $841 times 15. Whoop. Uh-oh. I hit some other number there. Let's try that again. 841 times 15. 12,615 joules. So now we have the heat for both parts. You see that? We have the amount of heat it takes to warm it up, and then the amount of heat it takes to boil it. We add those two numbers together, and we have the total heat for the process that's being requested by the question here. So total heat is going to be the sum of the two processes. First, heating it up, and then boiling it. And I added that up over here, get 14,571 joules. So that's the total amount of heat or total amount of energy that it takes to both heat that 15-gram sample of ethanol up and boil it. The problem on the lab was the opposite of that, because you were condensing the steam and then cooling it down, but the same idea. You had two steps. You had a phase change going from gas to liquid or liquid to gas, and then also a change in temperature. The phase change happens at constant temperature. The changing temperature obviously happens at changing temperature. What do you think about that? Everybody's looking at me like, no. All right, I think you should try one. Let's find another good one. All right. I'll look up these values for you, or I'll give them to you. But I want you to calculate the amount of heat energy in the following, and we're just going to do B. So skip A for now. You can go do that one as part of your homework. But let's just look at B. The kilocalories released when 15 grams of steam condenses at 100 degrees, and then the liquid cools to 0. So information that you need for this, you need to know that the specific heat of water is 1 calorie per gram degree C, which you should know. And you need to know that the heat of vaporization for water is 540 calories per gram. So think about the two parts of this question. It might help if you draw a heating curve type diagram like we did in the last one. What's happening? And then calculate the two parts and try to come up with a total and work together, or however you want to do that. What does the heating curve look like? So can I air draw it? What would the heating curve look like for this? Yeah, okay. Just kind of doing it right. It would be kind of straight across while it's condensing, and then drop it down. Because the temperature stays the same as it's condensing, but the energy is being released, and then it goes down. Another way you could think of it is the same as a heating curve, so like this, but you're going the other way on the curve. If you think about the previous one, it's really the same kind of curve. Just opposite. So you go like, you'd be starting here and going this way and then down this way. Think about that and then how you would calculate those two parts. All right, what kind of numbers are you getting for this? I don't know the answer, so I don't know if you're right or not. Anybody get anything? Number? So we're gonna.
Simple question.
Mhm.
When you use anything to go on the cooling or freezing, do you use negative number?
No. Well, you can. It doesn't really matter because here's how the question's worded. It's worded kilocalories released. So that's kind of like saying the opposite. But you're right that technically that could be expressed as a negative number because it's like the calories are going the opposite direction. And so in a more careful and technical heat calculation, yes, you would keep track of which direction the heat is going, and you would express exothermic processes as negative amounts of heat and endothermic processes as positive amounts of heat. So yes, you are correct. However, in these types of problems, we usually don't worry too much about that. Like you should get the same number either way. It's just whether or not it would have a negative sign on it. So if I graded a question like this, I would not I would not mark it wrong if it was negative or positive, as long as the magnitude of the number is correct. It should be fine. All right, so let's look at these two parts again. This time the first part is the phase change, because first the steam has to condense before it can cool. It has to turn from steam to water, and then it cools down. So the steam to water part is using the heat of vaporization. So we've got 540 calories per gram. And this says kilocalories. We'll just stick with calories for now because that's the numbers we've got. And then if we want to convert it at the end, we can convert it at the end. So that's 540 calories times 15 grams. 40 times 15 is 8,100 calories. And that's, we can be more specific, 8,100 calories released when the steam condenses. And then the second part is the cooling. And that's done just like all the other cooling problems. So we take our 15 grams, 15.0 grams, times the change in temperature, which here is 100 degrees, because it's going from 100 to 0, times the specific heat, 1 calorie per 1 gram degree C. And that's 1,500 calories. And that's released when the water cools. So you've got the heat released when the steam condenses, and then the heat released when the water cools. And this is the same as what was on the lab. Add those two together. It's 9,600 calories total. Is that what you got? Good. And that's also then, we could report that as 9.6 kilocalories. Okay. So move that decimal place over 3 spots or divide by 1,000, however you like to think about that, and you've got kilocalories. Good? All right. All right, let's move on then. So keep working on these types of problems. This is as hard as it would get, really. That these kind of 2-part or multi-part problems with a phase change is as fancy as you're going to see from this chapter. So now we've done a couple of them. Hopefully you have a little bit better sense of how that goes. All right. This next chapter that we're going to get into is a little different in that we're going to start talking about the structures of atoms and ions. Sadly, there's not as much math involved, so I hope that's okay with all of you. But there will be counting. Is that good? And a little bit of like addition and subtraction. But usually people like that a little better. So, all right. So we got the periodic table up there. What does that mean? Anybody know? What does that represent? We talked a little bit about states of matter and how we have elements, and that's the elements. Anybody know anything about the rows or columns or the blue numbers or the red numbers or anything like that? Yeah, what do you know?
The blue ones are their numbers.
The blue ones are their numbers.
And then the bottom ones are their weights.
Yeah, the blue ones are called atomic numbers, and the red ones are called atomic weights. Okay, what does that mean? Yeah, you're right. Okay, anybody know? What do those numbers refer to, or those weights refer to? Yeah. The atomic number is the number of protons in the element. Anybody else know that? You heard that before? Does anybody know what a proton is? Positively charged, right? So we'll have to look a little bit about the structure of an atom itself to figure out what these things mean and why they're important. So anybody want to give me a basic picture of the atom? What does it look like? A circle. Okay. Anything else?
With some pluses and minuses.
A circle with some pluses and minuses. Yeah, that's about right. What are the 3 things in the atom? We talked about protons. What else is in there? Neutrons and electrons. Oh, good. Okay, so you know this. So an atom is made up of protons, neutrons, and electrons. The number of protons gives us what we call the atomic number. You see up in blue on that periodic table, up in the upper right-hand corner. And it also gives us the identity of that atom. You'll notice there are no repeats with blue numbers up there. So any different number of protons means you have a different kind of atom. So if you have 6 protons, if you have a particle with 6 protons, no matter what else it has, we call that carbon. We call that a carbon atom. And if you have a particle with 7 protons, we call that nitrogen. Even if everything else is the same or different or it doesn't have anything else or whatever, the number of protons tells us what the atom is. So what do these other things give us? What do we have if we put the protons and the neutrons together? Yeah, the protons and the neutrons together are going to be mostly the weight. Or we'll say mass is really a more correct term, but weight's okay too. It's true that electrons also have some mass, but their mass is so small compared to the mass of protons and neutrons that we can effectively ignore it and say that only the protons and the neutrons really contribute to the mass. Where are these particles in relation to each other? Somebody said something about that. The nucleus? They're all in the nucleus? Okay, right. So the protons and the neutrons are in what we call the nucleus, or the center. And then the electrons which are negatively charged occupy this space around, actually really far away from the nucleus. And the old picture is that they orbit the nucleus like planets, like they're spinning around in a circle. That's not actually true. We know that's not really what they do. They don't follow these trajectories, but they exist in these areas outside the nucleus. And we'll talk a little bit more about that when we talk about that structure. So electrons are negatively charged. Protons are positively charged. And the electrons are actually really far away, relatively speaking. The distance between the electrons and the nucleus is about 10,000 times the size of the nucleus itself. So if you imagine if our nucleus was 1 meter across, which is this, if this were the nucleus of an atom, the electrons would be found 10 kilometers away. Yeah. It's far away, right? That's like 6 miles. So that means that most of all matter is made up of what? Volume-wise. Yeah, nothingness, just space. Because it's mostly just space between the nucleus and the electrons. So most of all that we experience is really just nothing. And the mass is only really taking up a small amount of that space. So I like to think about that when I want to think about something kind of scary. What? It's sad?
The way you said that.
Well, I don't know. It's amazing. Like we all kind of exist and mostly everything is just nothingness. I don't know. Think about it next time you're high. It makes more sense. So anyway, we have this structure of this atom, and that is reflected in the periodic table. But we have one problem that we haven't quite worked out, that the numbers on the bottom, those atomic masses, are fractional. But we can't have fractional, or we don't have fractional subatomic particles. In other words, let's look up, for instance, at carbon. Carbon, the mass is given as 12.011. But if a proton weighs 1 and a neutron weighs 1, and a carbon atom has 6 protons and 6 neutrons, why is it 12.011 and not just 12? Does anybody know? There aren't fractions of neutrons. What?
It has to do with their isotopes.
Right, it has to do with this thing called isotopes. So let's look at this. Each proton and neutron weighs 1 atomic mass unit, or AMU. It's a measure of mass like grams, but it's a very small one because we're dealing with protons and neutrons. And it's standardized so that each electron, or each proton and each neutron has 1. So that means that a particular carbon atom would have, let's say, 6 protons and 6 neutrons, and we would call that carbon 12. We write that with a little 12 in the upper left-hand corner, and we would call that carbon 12. And this tells us that it has, at 12 there, tells us 6 protons and 6 neutrons. Now there's a lot of numbers that add up to 12. How do we know it's not 7 protons and 5 neutrons? Right, because if it had more than 6 protons, it wouldn't be carbon anymore. It would be nitrogen in that case. So the fact that we wrote a C tells us it has to be 6 protons. And we can look that up. And don't worry if you don't know the names of the elements. When we do quizzes and stuff on this, I think I have somewhere in here. I'll bring some from upstairs. We'll use periodic tables that have the names on them, so you can look them up that way. But that tells us 6 protons and 6 neutrons. Can we find out how many electrons are in there too? Yeah, the protons are positively charged and the electrons are negatively charged. So if this atom is neutral, if it has no overall charge, that means that the protons and the electrons have to match. 6 plus 6 minus is 0 overall. So this is a neutral atom in that it's not charged. And so we can also assume that there are as many electrons as protons. Now, we still haven't answered our question about the 12.011. The reason for that is there's another type of carbon called carbon-13. Now, how many of each type of particle would be in carbon-13 based on what we just did? 6 protons, 7 neutrons, and still 6 electrons because it's still neutral. There's no little plus or minus written up there. We'll get to those soon. So hold on a second, I just wrote it wrong. Pay attention. Thanks. So carbon-13 looks pretty much the same, except each atom of carbon-13 is going to have 1 extra neutron. And the name for the relationship between these two types of atoms is that they are isotopes. Isotopes have the same number of protons and a different number of neutrons. Isotope means same type, so they're still called carbon, but they have different atomic masses. And what happens in nature is that there's a mix of these different isotopes. Some isotopes are more common than others. In the case of carbon, carbon-12 is about 99% of all the carbon. Actually more than that, like 99.9% of all the carbon. But there's a little bit of carbon-13, and there's actually a little bit of this carbon-14 also. And so when you average all that together, you get a little more than 12. And that's where that 12.011 comes from. We don't deal with individual atoms very often because they're tiny and you can't really, well, you need some special, now you can manipulate them with some special equipment, but we don't usually do that. Usually we take a scoop of something, which is going to have lots and lots and lots of atoms in it. So when you take a scoop of something, you can assume that all those atoms have this decimal average mass, even though each individual atom might have a slightly different mass, like 12 or 13. So if the mass is given, like if the specific isotope is given, like carbon-12 or carbon-13, you can calculate the number of protons, neutrons, and electrons. If that number is not given, you can't. So if I said how many protons are in a bromine atom, that's number 35, Br, that you can answer how many protons are in a bromine atom. 35, because that's the atomic number. But if I asked you how many neutrons are in a bromine atom, what? Yeah, you'd say which bromine atom or which isotope, because we don't know. We can't know from that number that's up there. In fact, that number might be misleading because you'll see it's like 79.9, if you can see over there. So you might think, oh, the most common isotope of bromine is 80. Actually, there is no bromine 80. There's bromine 79 and there's bromine 81. And they're about half and half in nature. So they average out to be 80, even though there's no actual bromine 80. What if I asked about electrons in a bromine atom? How many electrons in a neutral bromine atom?
35.
35, right, because it's got to offset the number of protons. So, good. Okay, let's talk about electrons a little more now, because that's actually more what we care about. And when I say what we care about, not that this stuff isn't important, but what the processes that we call chemistry, the combining of atoms, the making of new things by combining those atoms, that all has to do with electrons interacting with each other. The nuclei are not really changed except in nuclear reactions, which we'll get into near the end of the semester. What we really care about for the chemistry is the electrons. So we already talked about that in a neutral atom, the number of electrons is the number of protons. And what about when that's not the case? we have something called ions, which are charged atoms. And that charged atom comes from an imbalance of protons and electrons. What kind of an ion do you think you would have if you had more protons than electrons? Would it be a positive ion or a negative ion? Positive. Protons are positive, electrons are negative. So if you have more of the positive protons, you'd have an overall positive charge. And if you had more of the negative electrons, you'd have an overall negative charge. So we've got two terms for those. Anybody know what they are? What positive and negative ions are called? Yeah, anions and cations. So anions are negatively charged, which means they have more electrons than protons. And then cations are positively charged with more protons than electrons. So you should know those words. We'll use them a lot. So let's look at an example. A sodium ion, Na+, would have how many protons? 11. We can look that up on the periodic table. If it were a neutral sodium atom, how many electrons would it have? 11. But since it has a positive charge of +1, how many electrons should it have? 10. Right? One fewer than the number of protons. So that gives it its little positive charge. Now notice the order that I did that in. We looked up the protons first and we wrote it down, and then we figured out the number of electrons based on what the charge has to be. That's an important thing to remember, because a common mistake on this that people do is I'll say, all right, what are the numbers of protons and electrons for this ion? If you look at the electrons first, it's not going to be right because you're going to come up with 12 protons. And we can't have a sodium ion with 12 protons. Why not? Yeah, it wouldn't be sodium anymore. It would be Mg, magnesium. So you don't want to think of positive ions as having one extra proton, because that kind of leads you to increase the proton count by 1 when really you want to decrease the electron count. So think of a positive ion as lacking in electrons, as having too few electrons. On the other side, we could have an anion, a negatively charged ion like chloride. How many protons and electrons would a chloride ion have? $18 electrons? Okay, yeah. So it would have 18 electrons, 17 protons, and 18 electrons. One more. We can also have ions with higher charges. If we have a higher charge, you'll see them written a couple different ways. This is kind of the standard now, and this is how you'll see it in the book, where the number of positives or negatives is written just actually before the sign. But you might also see it like this, or like that, with actually 2 positive charges. They're all fine. They're all correct. The first one is more standardized because it's less confusing if there are other things coming after it. You could imagine the Ca+2, and then if there's something else next to it, it's hard to tell if the 2 goes with that or if the 2 goes to the next thing. So that's why the first one has become more standard, but you may see any of those 3. How many protons and electrons would that have? 20 protons has to be because it's Ca. And then how many electrons? And 18 electrons. Good. Yeah. All right, so you think you can do that? All right, we'll try one more. Let's try phosphide ion, P3 minus. How many protons and electrons would that one have? What do you think?
15 protons.
Great. So what do you think? Agree? 15 protons, 18 electrons? Yeah. Right. So you got 3 more electrons than protons. Okay. This all becomes important because we need to think about how these electrons are arranged inside the atom. And that's actually going to be a really powerful way for us to predict what kinds of ions different atoms can form. The way we do this is by assigning something called an electron configuration. And it tells us how the electrons are arranged in the atom. There are various levels of complexity that we can get into involving electron configurations. We're going to take kind of the more basic approach, mostly because it's still very predictive, and we can still find the information that we need from this approach. If you have done this kind of thing before and you think like, wait, something's missing, the answer is yes, something is missing. If you want to talk about that, I'd be happy to talk about that later, but it's a little bit beyond what we need in this class. So we're going to look at electrons in terms of what I like to call buckets. They're really energy levels. If we imagine energy from lower to higher energy, and then this x-axis is going to be the distance from the nucleus. As electrons get farther and farther away from the nucleus, they're not held as tightly because the nucleus has the positive charge, the electrons are negative. So the closer they are, the stronger they're held by the nucleus. The further away they are, the more weakly they're held. So the ones closest to the nucleus are the most stable and therefore the lowest energy, lowest potential energy. The ones farther away have higher amounts of energy, which also means that they're the ones that can do the chemical reactions and can be more reactive. So we're going to look at 3 buckets, that is 3 levels at which the electrons can exist. The first level we'll draw down here, and the second level up here, and then the third level up here. And then there's 3 numbers you need to remember. 2, 8, and 8. And that's the capacity of our buckets, or the capacity of our levels. And this tells us that in the first level, there's only room for 2 electrons. So that little circle is going to be our electron. There's only room for 2 electrons in that first bucket, in that first level. In the next one, there's room for 8. And then the last one, there's also room for 8. Or in the third one, there's also room for 8. Now, we can assign electrons to those buckets by building them up from the lower to the higher buckets based on what atom we're talking about. So let me show you an example. We'll draw another one of these things with our buckets. And we'll look at a carbon atom. How many electrons are in a neutral carbon atom? 6, right? 6 electrons. So we can build up these electrons until we get to 6. And that's really all you have to do. So we'll start with the first 2. 1, 2, 3, 4, 5, 6. And this tells us that there are 2 electrons in that first level and then 4 electrons in the second level. We're going to give those levels some names. Anybody know what the highest level that has electrons in it is called in an atom? Valence, yeah. So this is going to be our valence shell or valence level. And this has the outermost electrons, the ones that are furthest from the nucleus. Those are the most reactive. Those are the ones that do all the chemistry. So we're often going to need to know, to be able to predict these things, we're going to need to know how many valence electrons does a particular atom have. And to find that, we put them in their buckets, and then we look at how many are in the outermost one, or the highest level one. Okay. So I want to try the same thing. Oh, sorry, one other definition that we should have. The ones that are not in the valence shell, the ones that are shielded and closer to the nucleus, those are called the core electrons. And that includes all the levels that are not valence. So the valence is just one level, whatever is the outermost level, and all the other ones inside are called the core. All right, so now I want you to try a couple. I want you to draw a configuration for sodium and for a sodium ion, Na+. And I want you to answer these questions for each of those. Actually, just one question. How many valence electrons in each? So you're going to need to figure out the number of electrons total, and then populate the buckets and count how many are in the highest or outermost bucket. When you think you've got those numbers, turn to the person next to you or around you and see how everyone's numbers look. See if they match. If they don't match, talk about why they don't match or what you think. Are you getting the same kinds of numbers? All right, while you do that, I will draw these. This is what your configuration looks like for a neutral sodium atom. 11 electrons, 1 in the outermost level, so 1 valence electron. All right. A sodium, same colors here. A sodium ion then is going to be a little different in that it has 10 electrons. Did you get 10 electrons for the sodium ion? Okay. I know we did that one earlier. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many valence electrons for the sodium ion? 8. So big difference.
You already said this, but do you write that minus after the E just because the electrons are negative in charge?
Oh yeah, sorry. Yes. Oh, this kind of abbreviation for electron is an E with a little negative sign because it's negative. You don't.
It's negative even without it.
It's negative even if you don't write the little thing. I've just gotten in the habit of doing that because that's kind of like a standard symbol. But if you just write an E, that's fine. But when I use that symbol, that will mean specifically electron. Thanks. So let's look at the difference between these two then. It's totally changes shell. And not only does it go from 1 to 8, but now the sodium ion has a full shell, a full bucket, a full valence shell of electrons. And that actually gives it a special type of a stability. So we have this rule that based on this. And it's called the octet rule. Octet comes from 8. It means that atoms want to have 8 electrons in their valence shell. The way I paraphrase it in our example here is full buckets are happy buckets. Meaning that an atom is going to be more stable if it has a full bucket, a full valence shell, than if it has a partially full one. And you can see this pretty dramatically. Well, we'll take a break, and then when you come back, I'll show a video where you can. I would do a demonstration, but they don't like things blowing up too much down here, so we'll just watch a video of it and stick to that. Let's take like 15 minutes or so. We'll come back and take a look at that. I'll try to get up and get the quizzes. That's right. Okay. Someone trying to increase strength is told to eat protein. I think the same question was on the practice quiz on Blackboard, just with some different numbers, but the same idea. You've got two numbers, 180 grams of protein versus 5 ounces, and the question is asking you to compare those. Is the 180 grams smaller than the 5 ounces? In other words, if somebody eats 5 ounces, is that at least 180 grams? This is not an easy question to answer until we have those units in the same type of unit. So instead of grams, we could put them both in ounces, or instead of ounces, we could put them both in grams. People pretty much did, it was about 50-50 which way you went. Anybody want to see one in particular? Did you go gram? Who went grams to ounces? Let's do it this way. Who went grams to ounces, if you remember? Ounces to grams? So mostly ounces to grams. All right, we'll do it that way. So 5 ounces. Now ounces to grams, it would be nice if we just had a number that told us so many ounces equals so many grams. Then we could just do that quick conversion and we'd be done. But sometimes you don't have that number. And in this case, we didn't. So we have to figure out how we're going to get from ounces all the way to grams. So we look at what we do have. We have ounces and pounds. We have pounds and kilograms. And do we have kilograms to grams? Well, it's not given, but we should know that because there's 1,000 grams in a kilogram. That's one of the prefixes that you need to know. So we can go ounces to pounds, pounds to kilograms, and kilograms to grams. So then you set up the conversion, 5 ounces. And then we're going to get rid of ounces and have pounds. Right? Cancel ounces and make pounds. Cancel pounds and get kilogram. And cancel kilogram to get gram. So now we have to fill in all those numbers. Ounces to pounds, that's given in the constants over here. There are 16 ounces in 1 pound. Kilograms to pounds, that's given as well, 2.2 pounds to 1 kilogram. And then we need to know that there are 1,000 grams in 1 kilogram. To calculate that all out then, we get 5 divided by 16. So we divide by everything on the bottom, multiply by everything on the top. 5 divided by 16, divided by 2.20, and then times 1,000. That gives us 142 grams. So 5 ounces is 142 grams. If a person has eaten 142, have they made it to 180? Doesn't look like it, right? So the answer is no. 142 grams is less than 180 grams. So this person ate less than 180 grams. All right, 6.820 millimeters is the same distance as. Now this one, we could go through and do all the conversions because these are all numbers that you should know, well, except for inches. But you should know how many centimeters, we should know milli, centi, and kilo. So you could go through and do all those conversions, but there should maybe be a way that we can think about this first and maybe make it a little easier on ourselves than having to do every calculation. So we can think about how big is 6.8 millimeters? If you're gonna, it's like little, right? Yeah, like that. Remember the millimeters were those smallest lines on the ruler? So if you figure 6.8, about 7 of those is like that. So we can look at these other measures and say, well, which ones of these are definitely not about that much? So is that 68 centimeters? Probably not, right? 68, we know a centimeter is about like that. 68 centimeters is going to be like that. So that's not going to be the same. So we can cancel that one out. What about 6.8 inches? Probably not. How big is 6.8 inches? Yeah, about like that. So we know it's not that's not the same as that. And what about 0.68 centimeters? Yeah, maybe. 0.006820 kilometers. I don't really have a good sense of that, so I'm just going to say I don't know. And then the same thing with the meters. So I'm not saying we can't figure those out, but the A and B can be eliminated right away just by saying that's clearly not the same amount. The other ones we're going to have to check. So we can check these by doing those conversions. We can also see that between D and E, only one of those is going to be correct because a kilometer is not the same as a meter. So they can't both be the same thing. All right, so we'll look at those. You can go through and do those conversions. So there are 10 millimeters in a centimeter, which means that we would divide by 10 to go from millimeters to centimeters. So C is one of the ones that is the same. And then there are 1,000 millimeters in a meter. So we would divide by 1,000 and see that this is also the same. So the answers were C and E. If you got one of them, you got 1 out of 2. But if you got one of them and then also picked a wrong one, you didn't get that partial credit. So, what is the proper volume measurement on the graduated cylinder? So this one went pretty well. A couple of types of errors. I think the major error here was assuming that this scale was something that it wasn't, which is assuming that every tick was 0.1, which is not the case in this particular apparatus. And then the other mistake was not having the right number of decimal places. So let's talk about how we would get that. When you're first look at an unfamiliar scale like that, the first thing you have to do is figure out what do each individual tick mark represent? What does each tick mark represent? How big of a difference is there between each? In this case, we'll assume this is milliliters because it says graduated cylinder. So we've got a 6 here, and that's this line, and then we've got an 8 here. But what does that tell us about that space in between? Yeah, that right here has to be 7, that it has to go, if the larger difference is between 6 and 8, then the midpoint of 6 and 8 is 7. That's always going to be true. So even though that 7 is not given, we should be able to see that just by knowing the 7 comes between 6 and 8. So then we can go further here, and we notice that between two numbers like 7 and 8, there are 4 little tick marks. So you've got 7 and then something, 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 8. So what does that increment have to be? 2, or 0.2 in this case. So one thing that can be helpful in these types of problems is to actually write out what each of those lines is going to represent. Because if your first guess was that it would be 0.1, you'd quickly realize that you were wrong when you went 6.1, 6.2, 6.3, 6.4, and then you were supposed to be at 7, but you weren't quite there yet. So if you actually write them out, that gives you a kind of a hint as to whether you're in the right spot or not. So to me, on that screen, the very bottom of this liquid seems to be right about there, which I would say is pretty much right at the line, maybe just above the line. Would you agree? So that tells me that it is 6.60, or maybe 6.61, maybe 6.62, depending on how you looked at it. The copied sheets might have been a little bit different too, but something around that range. If you were up into the 6.7, 6.8 range, I probably took a point off because that's starting to get a little far away. And if you were somewhere, or you got the wrong number of decimal places, or kind of way off, then you didn't get any of those points. So remember that we always have to use our marks and then add 1 decimal place beyond where the marks tell us that we've estimated ourselves. All right. And the final question, this is what we did in lab the first day. A graduated cylinder contains 155 milliliters of water. We put in this 15-gram cylinder of iron. What is the new water level in milliliters? Anytime you see a problem like this, it can be helpful just to kind of visualize what's actually happening here. So you've got a graduated cylinder with 155 milliliters of water. If there is a little metal cylinder that gets dunked in, just like we did in lab, what happens to that water level? It's going to go up a little bit, right? We don't know how much. We have to calculate that, but it's going to go up a bit. Some answers were wildly off from that idea, and I could tell this you're just kind of trying to plug in numbers into equations without really thinking about what was going on. And that's a really common thing in chemistry. You can really help yourself out if you think about what's happening. If there's 155 milliliters of water and we dunk something in, is the new water level going to be 0.5 milliliters? Probably not, unless it splashes out or something, but it doesn't say that. Or is the new water level going to be like 5 million milliliters? Probably not. So if you come up with some number that seems completely inappropriate for the question, chances are it is, and you should go back and check what you did. So in this case, we want to figure out how much space that iron piece would take up. And then when it's put into the water is going to rise by that much, however much that piece of metal takes up. So how do we find how much space something takes up if we only know its mass? The what? Yeah, the density will give you that volume, and that's the space that it takes up. So the cylinder of iron is 15.0 grams. But we can multiply that by a quantity that gets us rid of grams and instead gives us milliliters. So that's 7.86 grams per 1 milliliter. And if you divide those out, you get something like 1.9 milliliters for the piece of iron. So the iron takes up about 2 milliliters worth of space, which means if that iron gets put into that cylinder, into that water, how much is the water going to go up? Yeah, by that much. So 155 plus 1.9 is, 156.9 milliliters is that new level, or 157 milliliters, which is what we did in lab. You put the metal piece in, the water went up, and from that amount that it went up, it allowed you to figure out the volume of that piece of iron. And when you know the volume of the piece of iron, then you could find its density, and that's how we did it in lab. Questions about any of those problems? All right. We will probably have about 8 quizzes, and we'll drop 3. So you can afford to have some rough ones if this one didn't go as well as you would like. If you did well on this one, as many people did, great. You have one good one in the bank.
Are we going to review for the quiz?
Are you going to what?
Review for the quiz on Wednesday?
What do you mean?
I thought you said you were going to go over what the quiz was going to be about.
Oh, yeah, at the beginning.
Okay.
That we can do more if you have questions, if things from the homework, but it'll be these kinds of things, these heat things, whether something is exothermic or endothermic, those kinds of ideas. Yeah. All the homework from chapter 3.
Is there a review, from last semester? Like you did?
Yes, there should be one up there. It may not be exactly the same because the weeks might have been a little different or something, but all of the quizzes from the last year are up on Blackboard. Is it different? Okay, so we must not have done a quiz on that topic last time. But I'll pull it right from the homework from chapter 3. All right, let's talk a little bit more about electrons. So we were just finishing up, and I said I had a demonstration of this. So let me see if I can find that. Actually, before I do that, I have to change the. I think that's right. All right, let's see if I can get this to work. That's the sodium metal over here. Sodium ions, what happens when you put sodium ions in water? You know? I would show you a video, but it's not very exciting. That's salt water. So if you put salt in water, that's sodium ions dissolved in water. Is it as spectacular usually? Probably not really, right? And the electrons tell us that. The electron counts tell us that. Sodium is so reactive because that one electron off by itself in that third bucket makes it very, very reactive. It really wants to give that electron up, get rid of it, and become sodium plus, where it has a full shell, which we've said is more stable, more happy. Full buckets are happy buckets. So if it gets rid of that one electron, it comes back to its happy bucket, and then it's not as reactive anymore. It's kind of done reacting. The reason I show you that and the reason we talk about that is this becomes a very powerful way of predicting formations of ions. If we think about this rule that we want to have full buckets, and what do we do to make our buckets full, we can look at many of the atoms on the periodic table and figure out what their most common ion is. So let me give you an example. Let's look at sulfur. S. Can we find it? Up there. Now, how many electrons does a neutral sulfur atom have? 16. So same exercise as before. Do the electron configuration, that is, figure out the electron counts, and then determine how many electrons would either have to be lost or gained for sulfur to have a full bucket. And that is the most common ion. So first, draw the electron configuration for sulfur. And then how many buckets would you add electrons to, or how many electrons would you add to it or take it out to make a full bucket? And then what would be the charge of that ion with the full buckets? There's actually two answers to this, depending on how you count your electrons.
I have a question pertaining to the salt. Wouldn't they be taking this table salt money, but isn't it sort of chloride?
Yeah.
That wouldn't be as reactive.
Well, it's the ions can't be really by themselves. So you can't just have sodium ions. You need something negative to go with them. And so with sodium, yeah, you could have sodium. But anything with sodium and something else, when you dissolve it up in water or put it in water, you just have those sodium ions. So you wouldn't see any kind of reaction. So what did you find out for sulfur? What would you do to the electrons to give it full buckets? Add 2 or take out 6. That would be the two answers, right? So you could either do this. Oops, I don't know why I just filled everything up. Sulfur has 16, so that's like this. So we could add 2, or we could take those last 6 out, and that would give us full buckets. Now, normally, as you seems like you figured out, you'd go with whatever the smaller number is. So it's easier. It's going to be easier to add 2 than to take 6 out. So the most common ion of sulfur is sulfur 2 minus, and that's real. That's correct. That is the most common ion of sulfur. So we can use this theory, this idea of how the electrons are set up in the atom, to figure out what the most common ions of various elements would be. All right, so what about, do the same thing with, what do we do? We did let's do aluminum, Al. Same question. What's the most common ion of aluminum?
I have a question. When it's like another, that has a higher number, like calcium, let's say, would you just keep adding buckets?
Good question. So yes and no. Yeah, as you and probably several of you realize that we had 2, 8, and 8, but there's more than 18, a lot more than 18 elements. So yeah, the answer is it gets more complicated. So yes, there's more buckets, but actually it turns out that the third bucket can hold 18, and you just get the first 8, and then it goes to the fourth bucket, and then it goes back to the third one for a while, and then back to the fourth one, and then up to the fifth. And so we just decided that's where we're going to stop it in this class. But if you go on and take general chemistry, or if you're just curious about it, I can show you how the whole thing plays out. We're just going to leave it at that for this class. Yeah, good question. Good job spotting that. So what'd you come up with? What's the most common ion of aluminum? 3? 3 plus? Yeah. Aluminum's most common ion is Al3 plus. So you can always figure this out by, well, for those first 3 rows anyway, putting those in. All right, here's another question. What about hydrogen? Is that a sound of joy or a, didn't sound like it? No. Okay. Hydrogen is going to be a little bit different because how many electrons does hydrogen have? Just 1. So you probably don't have to actually write it, but we could think about it. So what are you going to do with hydrogen? Get rid of an electron, add an electron? Get rid of, add? Well, the answer is both, actually. Hydrogen can form 2 different types of ions. It can form an H plus ion, which is actually more common, and that has no electrons. Hydrogen has no neutrons either, so actually an H plus ion is just a proton. So sometimes we just call it a proton. And we'll get into that when we talk about acids and bases. And then there's also H minus, which is called hydride, which has 2 electrons. So those are the common ions of hydrogen. All right, so why do we care about what is the most common ion? Part of it is that we can now make compounds and figure out how many of each element we need. Remind us what are compounds? More than one element, right? Put together. Ionic compounds are going to be more than one ion held together by what we call electrostatic forces, which are just the fact that positive and negative attract each other. But they're going to be multiple ions that we put together. So just putting ions together. And then the key for putting these things together is that the overall charge should be 0. So overall, the compound should be neutral. That's why they make the compounds, because the ions don't want to be on their own charge. They want to, it's more stable if they're together. So Some of these are really easy. Like sodium and chloride, you've got 1 plus, 1 minus. So they go together. We write those symbols together like this, and we have NaCl, or sodium chloride. And we'll get into the names next and talk about how we name those. But sometimes the charges don't match up. So let's say we have a sodium ion and an oxide ion, which is O2 minus. How are we going to make a compound whose overall charge is 0 if we have 1 plus and 2 minus?
Add another plus.
Yeah, add another plus. So we're going to need 2 of these to go with the 2 minus. 2 plus, 2 minus. Now the overall charge is 0. You see that? The way we write that is with a little subscript a little subscript number, saying that there are going to be 2 sodium ions for every 1 oxide ion. So that little 2 means 2 of the thing that comes before for every 1 of the other thing. What if I wanted a compound between aluminum, which we just learned was 3 plus, and chloride, which is 1 minus? How would you write that compound?
I have a question.
Yeah.
About one above it.
Yeah.
Would you ever give us the Na2O and make us go backwards?
Yeah, and see what the ions are? Yes, but to do that, you would have to kind of do what we did before. Like you have to figure out what the common ions were. And then, so for an example, let's say I gave you that and I asked you what are the charges on each of those ions. You would have to know one of them, like sodium. We know that sodium wants to make a +1 ion. And then we can calculate that the O must be -2 to balance out the plus. So you have to know at least one of them to be able to do that. And we'll talk a little bit about how to do that. There's kind of an order because some of them change and some of them don't. So what do you have for aluminum and chloride? Anybody get a compound? AlCl3. How'd you come up with that? Yeah, the 3 plus from aluminum, and then we're going to need 3 minus 1s to balance out a +3. So overall, in AlCl3, we have 3 plus and 3 minus.
So then is it, that works always like in vice versa like that?
I think so.
Okay.
I'm not sure. We might find some weird stuff, but let's try one that's a little bit different. What if we look at the compound between aluminum and oxygen? How can you build a compound between those where the charges balance each other out, neutralize each other? What would you come up with? You look like you want to say it.
So when you like use 3 oxygens there and then 2 AL.
Right. So you can't just change one of them because you've got 3 and 2. You can't make those equal by just changing one. So we're going to need 2 of these and 3 of these. So it's overall 6 plus and 6 minus. And to write that compound, that would look like this. Al2O3. All right. Now let's put all this stuff together. And let's write a compound for, and I'm not actually sure if this compound exists, but I feel like it probably does, so we'll try it. It's not one I've used before. Actually, let's write one that I know exists, because that's not really fair. So write a chemical formula, that's what we've been doing, for this compound, lithium nitride. So I'll give you the symbols. Lithium is Li and nitride is N. It comes from nitrogen. But I'm not telling you the charges. So you have to figure out the charges of these ions based on the electron counting that we just did before, and then put them together in the compound.
Just to clarify, in terms of like the most common, is that just gonna be like the least amount of electrons that you have to add or subtract?
Right.
Okay.
And that works for pretty much all of those first 3 rows.
So
For those
like
elements.
a problem like this, it's gonna be just the most common.
Right. Yeah, you're going to be able to use that. We'll get into, when we talk about naming next, we'll get into what happens when there are multiple possibilities for charges. You look confident. You got it. Anybody else feel good about this one? All right, what do you got? Still thinking? Hold on, a couple people are still thinking. We got a couple more minutes. What do you think is the most common ion for lithium? +1? How'd you get that? Doing the buckets? You found it has 1 valence electron, so you can lose that electron. Right. And what about nitride, nitrogen? What's its ion? -3, right. So what would the compound lithium nitride look like? Right. Li3N. Good. Okay. So the bucket thing works great, and I'm glad that's working for you. There is a little bit of a shortcut, and that is, I mean, it's nothing tricky, but that's the periodic table. So let me pull this into the notes so we can talk a little bit about that. All right, here's our periodic table, with a little bit more information than what we see up there. One thing you'll notice is these, the columns are numbered, and those are called groups, and the rows are also numbered, and those are called periods. What does it mean for something to be a period, or to be periodic? You know what that means? Not just in chemistry, but like anything. What does it mean for, what is that word? When we talk about something being periodic, what are we talking about?
So like periods in history.
Yeah, like what does that mean? Kind of like sections, or really it's a cycles, things that go over and over again. So if you talk about like a wave has a period because it keeps going up and then down and then back up again, and when it's gone from top to top, that's called a period. So same thing here. As we go through the row, we see different kinds of elements, and then when we get back to the beginning, we see ones that are like when we were at the beginning before. So it kind of repeats itself. And that's where these groups come in. You'll notice that there's 2 elements in the top period, the first period, then there's 8, and then there's 8. So that's like the buckets, right? 2, 8, and 8. So that means that elements that are on top of each other, elements in the same group, are going to always have the same number of valence electrons. And if we take number of valence electrons as predictive of chemical properties like ionic ion formation, then we can say, well, like everything, if lithium should be +1, sodium should be +1, well, really everything in group 1 should be +1. And that's true. That's what we see. That's what we observe. So all those, which are called the alkali metals, form 1+ ions. They also all have similar reactive behavior. We can watch another quick video of that if you'd like. Watch some more. So point being, all of those elements have similar chemical behavior, even though the kind of effect changes, they're still doing the same thing, doing the same types of reactions. And so we can say that for many of the groups. This one, so this next one's going to be all 2+, then 3+, 4, then like nitrogen and phosphorus are both 3-. Oxygen, sulfur, selenium, tellurium all make -2s, and these all make -1s. So it seems kind of time-consuming and cumbersome to do the buckets every time. But as you do that more and more, and you realize the periodic behavior, you'll not have to do that every time. So if you just remember that, say, chloride is -1, then you know that everything in that row is also going to be -1. Or in that, not row, in that column, it's going to be -1. So the periodic table helps you find those. Other stuff information that you see here that you don't see up there is the colors. So I didn't copy the legend because it didn't fit, but I guess I can get that. So it's in here. The blue ones here are what we call metals. The yellow are the non-metals, and the green are the metalloids. What does metalloid mean? What does it mean to say oid at the end of a word? Yeah, like ish. Yeah, like something is not quite one, not quite something. Like an android is something that's human-like but not quite human, or I don't know, what are other ones? Humanoid. Polaroid. Altoid? I don't know where that one comes from. Maybe it's the same. I don't know. We should look that up. So you've got your metals, non-metals, and then the in-between things that are kind of like metals and kind of not like metals. What are some of the differences between metals and non-metals? You know? You've certainly experienced both of those things in your life. If you saw something, what would make you think that is a metal versus that is not a metal? What would it do or look like, or how would it behave that would make you think that it was a metal? What?
It's solid.
It's solid. Yep, most metals are solid, although there are exceptions, like you can melt metal, right, and it's still metal. Mercury is liquid metal. What else? Because some of the nonmetals can be solids too. Nothing? If somebody handed you something and said, "Hey, is this made out of metal?" How would you figure that out? What would you think?
Well, I want to say because it's metallic, but
It's kind of the same thing. But I think where you go with that is like how you would look at, like, how does something look metallic? What makes something look metallic versus not metallic?
The weight.
Maybe the weight. So metals can be heavy, can be very dense, but some are not also. The shininess is part of it. Metals have a shininess to them that non-metals do not. The official word for that is a luster, that they have a luster. Just means that they're reflective, and non-metals tend to be more dull and not shiny. So that's one way to tell. Other ways are the physical behavior of metals. You could test electrical conductivity, whether or not an electrical current will run through it. A metal will carry an electric current. A non-metal generally won't. That's why things like wires are made out of metals. Speaking of that, metals also have the property of being able to deform without breaking. Have you ever taken a hammer to somebody's car? Really? Good. Okay. I wasn't sure if anybody would say they're like, yes, I do that all the time. You can try it later. Just go out to your car and just kick it really hard, and you'll see that it doesn't just shatter and fall to the ground. It bends, right? It dents. And that's a property of metals, that they can deform without breaking. So you can hammer a piece of metal and it will spread out and get thinner. You can pull it mechanically to make wires. And those are things that metals will do that non-metals won't. And then the metalloids in the middle are kind of both. They sort of look metal sometimes and sort of don't. They sort of behave metallic sometimes and they sort of don't. So how you can tell that is if you look at that little stair step that's on pretty much any periodic table. You'll see it here also if you don't have the colors. The elements right on the stairs are generally those metalloids or semi-metals, and the ones to the right are the non-metals, and the ones to the left are the metals. All right, another special group that we'll see here, way over on the right, we have the noble gases. These are special because they pretty much don't make compounds. With a few exceptions, they don't really combine with other elements. They're just kind of on their own. Why do you think that is? Yeah, they all have the full buckets. They either have 2 or 8 valence electrons. And so there's no kind of energy incentive for them to lose or gain any more electrons because they're already as stable as they need to be. So things like helium, neon, argon don't really form compounds with other elements. And that's predicted by their electrons. All right, so we've got all this stuff now. We know some ions. We know how to put things together into compounds. The last piece for tonight is going to be talking about how to give them names. We need to be able to talk about these things. And if we're going to talk about them, we need to know what each other are talking about. So we need a standard way of naming these compounds. before these rules that I'll talk about, it was kind of just a free-for-all. Whoever discovered something gave it a name, and it was usually named off of some property or something that it did. So everything just had its own name, and you just had to memorize a huge list of what everything was named if you wanted to know about chemistry. At some point, people realized that was getting a little cumbersome and ridiculous, and so now there's these very specific rules that will work for any compound, and anyone who knows chemistry should be able to tell you what that compound is, what its formula is based on its names. So here's how we name ionic compounds. First, the metal part stays the same. So you'll notice that all the ionic compounds we looked at are metals and nonmetals, one of each. That's a good way to tell an ionic compound, a metal and a nonmetal together. And the metal name stays the same. So like sodium stays sodium. Lithium stays lithium. Nothing changes. The nonmetal does change its name. It drops the end and becomes an ide. So chlorine becomes chloride. Oxygen becomes oxide. Sometimes it drops a few letters, sometimes just a couple. So chlorine becomes chloride. Oxygen becomes oxide, and so on. So nitride, phosphide, carbide, bromide, fluoride, selenide, all of those drop that and become the ide. And the ide tells you that that's going to be the anion. So the metal is always going to be the cation, and the ide, nonmetal, is going to have the negative charge and be the anion. And then the cation goes first. And if the metal can have more than one possible charge, we have to specify that. So I'm going to write that rule now. First, we're going to just look at some where that's not the case, and then we'll look at those special cases. So if the metal can have more than one charge, indicate the charge with a number, a Roman numeral in parentheses. So like 1, 2, 3, 4, etc. after the middle name. And I'll show you what that means, but I just wanted to put it up here with the other rules first. So let's go back, just the ones where that's not the case, the ones we've already talked about. Let's talk about how we could name them. So let's say we have CAS. What would you name that compound? Okay, go ahead. You said it too?
No, calcium sulfide.
Calcium sulfide. What do you think? Yeah? Sounds good, right? So let's make sure it follows our rules. The metal name stays the same, so Ca is calcium, that's calcium. The non-metal, the S, we drop the end of it and we make it ide. So instead of sulfur, it's sulfide. And if you didn't know the S was sulfur, that's fine. You know, you could look that up on the periodic table. So that would become sulfide. So CAS is calcium sulfide. So let's go back up to the examples that we just did and name these. We got sodium chloride. What would you call this next one? Sodium oxide, yeah. Notice we don't say how many of the sodiums there are. We don't say sodium 2 oxide or disodium oxide or something like that, because we know there have to be 2 to balance out the charge. So we don't need that extra information there. So it's just sodium oxide. What about this one? Aluminum chloride. On this one? Aluminum oxide. So you get the idea? And then that's how we got lithium nitride. All right, so let's get into that last category where it gets a little bit weird. What happens if the metal can have more than one charge? We talked about the group 1A having a 1 plus and 2A having a 2 plus and some of these ones that we can predict. But all the stuff in the middle, known as the transition metals, can have a variety of charges. They can actually exist in different forms. So let me show you an example. Iron. Anybody know the symbol for iron? Fe. Let's look at 2 different compounds of iron. These both exist. There's FeCl2 and there's FeCl3. If we just said iron chloride, we would not be specific enough because both of those are iron chloride, but they're clearly different. So we have to specify what kind of iron we're talking about. And when we say what kind, we mean what charge does it have. So this was kind of your question from before. Who asked that before? Is that you? Like what happens when you don't know a charge?
Go backwards?
Yeah, we have to work backwards. So if we have to figure out, we don't know the charge on iron because it can vary. It can have some different charges. So we have to look at what we do know and work backwards to figure out the charge on iron. So let's look at FeCl2. What is the charge on chlorine, on chloride? It's always -1 or 1 minus. All those in that 7A column called the halogens are always -1. So if you have FeCl2, it's overall neutral, and you know that each chloride is -1, and there's 2 of them. What does the Fe have to be to balance that out? +2. And then over here, we've got 3 of these. So what does the iron have to be? +3. So the way we name these 2, based on that, is we call this one iron 2 chloride. Whoops, I missed the E over here. And we call this one iron 3 chloride. So we got iron 2 chloride and iron 3 chloride. Notice that Roman numeral there, and this is a really common mistake, the Roman numeral is the charge, not the number of something. So how would you name this compound, Fe2O3? The Fe is iron, and the O is what? Oxide. But how do we know if it's iron 2 oxide or iron 3 oxide or iron something else oxide? We have to calculate the charge. So what's the oxide ion? What's the charge on oxide? -2. Yeah, we did that one earlier. That's the next row over from the -1s is the -2s. So if oxygen is -2, what does iron have to be to balance that out? +3, right. If we have 3, and you can always write these out if you don't see that. If you got 3 -2s, you need 2 +3s to balance that out. So that means that this one's going to be named iron 3 oxide. The 3 in parentheses is the charge on the iron. So that 3 plus, that gives you this 3. And that's going to be true. This is how you're going to name any compound that has one of the metals that doesn't have a fixed charge. So the ones with the fixed charge are the first column, which are all +1s, the second column, which are all +2s, and then there's a couple other weird ones that aren't quite in the right place. Aluminum is always +3, and there's a few kind of in the middle that we won't worry about. But basically, all the ones in the middle are going to be like this. So let's do some practice. I'm going to give you a couple different, if you have a periodic table or if you have one of these pocket telephones that you can look at the internet, you might want to pull one up so you can have some of these names. Let's see if you can come up with names for these 2 compounds. Actually 3. We'll do a third one down here. See if you can come up with names for these 3 compounds. If you got some names, start looking around and talking to people around you and see how they match up. You get those, I'm going to put a couple more the other way. I'm going to give you names, and you have to come up with the formulas. gonna go around. Flag me down if you have a question. If you have no access to a periodic table, this might be tough. But to help you out, those of you who did get a chance to look this up, what's PB? Lead. What's RH?
Rhodium.
Rhodium. That's used in, you ever heard of white gold? It's like a type of for jewelry and stuff. That's rhodium plated. Oh, you got some? That's rhodium plated gold. Often that's what the plating is. And so it can wear off over time and they can replate it with more rhodium. Fe is iron. And what's the symbol for platinum? PT. And what's the symbol for cobalt? CO. Okay, thanks. So those of you who don't have periodic tables, now you have those symbols to help you out. All right, we're almost out of time, so I do want to talk about a couple of these. All right, anybody feel good about any of these? You got them?
Can you show how to do the ones going like backwards?
So like the bottom ones? Yeah, let's do those first. So we've got platinum 4 oxide. Now that tells us, the platinum 4 tells us that, well, we can look up that it's PT. What does that 4 in parentheses tell us? The charge. So that tells us that this is platinum 4 plus. Now oxide, we're not told the charge of, but oxide's always the same charge, which is what? 2 minus. So we've got PT 4 plus and O2 minus. Now we have to make a compound out of those two that's overall neutral. So how do we do that? Yeah, we need another oxygen. So we need 2 oxygens for every platinum. And the formula that has 1 platinum and 2 oxygens is PtO2. So platinum 4 oxide would look like PtO2. Next one, same idea. Cobalt 3 tells us that it's CO3 plus. Oxide is 2 minus again. To make a 3 and a 2 equal, we have to have 2 of the 3 and 3 of the 2, as we've done a couple times tonight. Looks like that. And so that formula, when we count that out, is CO2 and O3. All right, so what do you have names for these then? Type them. What do you get for this one up here? Lead 2 oxide. Anybody get something different? 4. Why 2 or why 4? Anybody get anything different than either of those two? Well, let's look at it. Nobody, oops, feels super confident about that. We've got lead and O2. We don't know the charge on lead. That's one of the ones kind of in the middle there where we don't know what its charge is going to be, so we're going to use the parentheses. What is the charge on oxygen here? 2, and there's 2 of them, right? So that O2 means that there's 2 oxide ions that are each 2 minus. So what does the charge on the lead have to be to balance that out? 4 plus. So this should be lead 4 oxide. Because that number is the charge of the metal. All right, what about RHCl2? Right, that's rhodium 2 chloride. And then FeN2. It's going to be a tricky one, right? So iron, again, we don't know. Could be 2, could be 3. What about N? Yeah, N's gonna be generally -3 if it's just by itself in an ion like this. So we've got 2 -3s and then 3 irons. So what does each of those have to be to balance out those 2 + 3 or 2 -3s? +2. You see that? So these each have to be 2 to balance out all those 3s. And that tells us that this must be iron 2 nitride. Good question. When do you use the suffix 8? That is the next thing that we're going to talk about, which we don't really have time for tonight. So we're actually going to do this on Wednesday. Wednesday's lab is fairly short, so we'll finish up a little bit of this naming stuff, so that because the exam is the following week. So the first exam is a week from Wednesday. So those ions are called polyatomic ions, and they're ions that are made up of more than one atom together. So we'll get into those on Wednesday.